So in this part, we really need to understand the inner structure inside a heap, because we need to build a binary tree structure inside a heap. How to build a binary tree inside an array? Actually inside an array. So we call this whole thing heap. So let's see. Relationship among heap nodes. First, we need to describe heap nodes. You can only use array elements. How do you use array elements to represent nodes in a heap? All right, so let's look how do we store a binary tree inside an array. So here we can only do it by imagination, because you cannot visually see a binary tree in an array. So what you see still physically, the data is stored, is still in an array. But now you make some very special assumption to make it has the binary tree property. So that's what we plan to do. All right. First, let's look at the node representation. In a binary tree, we need to represent nodes. So each node, we make it correspond to an element in the array. So one node, that is one element in the array, we can use its index to locate, to specify its location. So located by its index. So that's one node. All right. If we know the index, we know where is the node. Okay? Yeah. Then when we consider relationship between two nodes, okay? Yeah. We just convert that relationship to another relationship between two indices, two array indexes. Yeah. So let me show you how to do it. Okay. Let's look at the parent-child relationship. So that's the typical relationship inside a tree. Yeah. General tree. Yeah. So here it's a binary tree. Okay. First, parent node P with index at I location. Okay. Then let's assume there are two child nodes, left child node and the right child node. For the left child node, we make its index or location at 2i. That relationship, 2-to-1 ratio, I to I, that relationship. For right child, we make the index at 2i plus 1. So you can see this kind of simple relationship. I from I, left to I, right to I plus 1. So simple. Yeah. All right. So in this way, we can describe parent-child relationship everywhere in a heap. Right? But here we need to consider a special case. The I cannot be 0. I cannot be 0. In a regular array, our index could be 0. No problem. But here, in order to have this special relationship, our I cannot be 0. Why? Because if we allow I equal to 0, if I equals to 0, 2i also 0, right? Then we have a problem, because two different nodes correspond to the same index I. That's not good. So we don't want that happen. So we do not allow two different nodes share the same index. So for that reason, we do not allow this. Okay? So now you can see in a heap, the first element A of 0 is never used. Okay? Is never used as any element in the heap, any node in the heap. Okay? Although you can use it to store some other different type of information, so that's okay, but do not use it as a node. All right. Next, heap property. After we define parent-child relationship, in order to make it support binary search, remember, in our first part, we need to consider binary search operation inside this data structure. So we need more property. So here we consider the heap property. Okay. All right. Two types of heaps. Yeah. So there are two types of heaps. Yeah. So very straightforward. The first, the max heaps. So the maximum element is at the root. Then when we go down, so we have the structure, some special order structure. Yeah. Similarly, min heaps, minimum at the root. Then certain structure, from there. Yeah. So let us define max heap property first. All right. Suppose we have one location with relationship like this, right? All right. Then we consider the values stored in these three nodes satisfy certain condition. So here we specify the first one, value at the root should be greater or equal to the value of its left child. That's the first inequality. The second inequality, the value at the root should be greater or equal to the value of its right child. Okay, yeah. So that's the max heap property. But here, the value between left, right child, we do not specify which one is larger, which one is smaller. So either case is fine. Left child has larger value or right child has larger value, both okay. Okay. So similarly, for the min heap property, just the opposite. We change the direction of the inequality, so we get that. So the value A of I less than or equal to A of 2i, and A of I less than or equal to A of 2i plus 1. Yeah. So in our discussion, we just use the max heap property. We assume we talk about max heaps, because the min heaps, we can use the same logic. Yeah. So we do not need to repeat it another time. Okay. All right. A max heap example. So now we really want to see what is a max heap. What does it look like? So we want to feel it. We want to get some concrete impression on this special data structure. Here, so let me give you an array. Remember, the first location cannot be used as any node in the heap, so we leave it blank. Then, the first element, that's the root of the heap, so we'll put value 16 there. Then, it has two child nodes at location 2 and 3. Okay, so we put two values. So the relationship specify in this way. We can also draw a binary tree like this. So we do some translation in this way. Okay? So here you can see it satisfies the max heap property. All right. Next, we consider node 2. Node 2 has 2 child nodes. Okay? Yeah. And we can draw the branches in that way. Yeah. Node 3, 2 child nodes, then we can draw 2 branches like that. Okay? Yeah. All satisfy max heap property. Yeah. Then node 4, 2 child nodes like this with max heap property. And node 5, 1 child node. So you can see the representation very straightforward. So, but this binary tree, it is imaginary. So you won't see it. So nobody will see it explicitly. What we can see is just an array in that way. But we can do the translation easily. Straightforward translation. So after the translation, you can see a binary tree. You can see a nearly complete binary tree. Okay, yeah. But in our program, we never need to do that translation. In our program, we just use the array, indices, relationship among indices to do the data processing. All right. So here we have a simple way to store a nearly complete binary tree. So, yeah. So we complete that. Okay. All right. So next, now let's look at how do we handle the dynamic data processing. Yeah. So when the data comes in dynamically, then sometimes the heap property could be violated. When the heap property is violated, we need to fix it. So that whole process, we need to keep doing all the time, on the fly. Yeah, because when the data comes in on the fly, so every time when we detect a violation, we need to fix it. So we need to maintain the structure, the heap structure, the max heap structure all the time. Okay? All right, so let's see how do we do that. All right, so when the heap property is violated due to some operations, insertion could violate that property. Deletion can also violate that property, right? Search does not. If you do a binary search, you'll never violate that property. Okay? The question is, when we detect a violation, how do we fix it? Okay. All right, so let's do some analysis here. Yeah. Violation occurs locally. Yeah. When we detect a violation, so think about this. At the beginning, we construct a max heap, so there is no violation. Then we need to use it to store dynamic data. Then suddenly, when we insert a new data item, we can detect at some node, the max heap property is violated. So that means violation occurs locally. Only at one node, it violates the max heap property. Okay. Number 2, local fixing operations. When we we fix that violation, we do it locally. Okay, we do local fixing operations. So what's that? All right. So we only consider the violation around that bad node, right? So bad node. But after we fix it, we need to change one of its child node. Then the violation could happen at that child node. So we try to detect and fix. Okay. So in that way, we always do that fixing operation locally. Okay, yeah, not globally. So we do not touch other parts in the tree. Yeah, otherwise it could be very complicated. So the local fixing this property will make our whole operation relatively simple. All right, here. All right, so make local violation assumption. Yeah, so that's reasonable because we start with a max heap. So after that, then we can make this local violation assumption. If we do not start with a max heap, then we cannot make this assumption. Okay, so we need to make it max heap first. All right. Here, let me use a diagram to explain that. Okay. All right, so suppose we have a violation here, right? Locally, yeah, and we make assumptions. For the left subtree, we have a valid max heap, and the left subtree we have another max heap. So no violation at the beginning. Yeah. The violation only occurs at this point. So we need to fix it. So when we fix, we may need to change the, values between P and L or P and R. One swap operation, one of the two possible swap operations. But when we do that, we may have another violation either here or there. Okay, so then we keep doing the same thing until we fix the problem everywhere. Yeah. Everywhere, things like this or like that. Okay, so that's the general procedure. Yeah. All right. Next, let's look at the details of this operation. We call it local heapify operation. Heapify operation. Make it a heap. So heapify operation. So we write a code. We write a pseudocode to do the things we described it in our previous slide. Right? So we use recursion approach, because we need to do that fixing operation all the way down to one of the leaves, one of the leaf node. Yeah, so that's why only recursion can make that representation very easy. Yeah. Let's look at the first method. Here I give you two methods, and let's compare these two methods after that. Right. For the first method, so let me describe step by step. Try to follow. Yeah. Although not too hard, but we need to follow, closely. Yeah. First, we compare values of these two nodes. If A of I less than A of 2i, this is a violation, right? So we detect the violation. It happens. After that, then we do one thing. Okay, we store this 2i in a variable called largest variable. Okay, we store it temporarily in that variable. Okay, all right. Else, the opposite, yeah. So actually, that's no violation, right? Yeah. In that case, we store I in this largest variable, right? Yeah. So in both cases, the largest contains the index of the node with larger value. Okay? Yeah. But that's not enough. We need to consider another pair. Okay? Yeah. A of largest less than the value of the right child. If that happens, we need to update the largest value with this index 2i plus 1. Okay? Yeah. Otherwise we do not update it. Okay? Yeah. All right. So after that, let's compare the value in the largest variable and I if they are the same or not. If they are the same, no violation, right? Yeah. If they are the same, that means no violation. Okay? So we do not need to do anything. So we only do something when they are different, not equal. Okay? So when they are different, we swap A of largest and A of I. Okay? So that's the whole procedure. But here you may feel, why we do so many comparisons? It looks like not the simplest way, right? Some of you may feel this is not the simplest way. Yeah. All right, so let me give you another way. So more straightforward, easier to understand, and it looks simpler. Yeah. All right. Method number 2. All right. Still, A of I less than A of 2i are not. Detection. Okay? If it is true, yeah, we detect a violation. So we swap A of I and A of 2i. Swap it immediately. Okay? So that's the first round. The second round, let's compare A of I and A of 2i plus 1. If A of I less than A of 2i plus 1, we make another swap operation. Okay? All right. So now, it looks much simpler, right? So think about the code shorter and easier to understand than method 1, method 2. Okay? But the question is, which one is better? So think about which one is better. Okay? From the understanding point of view, method 2 a little easier, but here we want to consider from the performance point of view, which one is faster? Better means faster. Performance point of view, okay? Which one is better? Okay. The answer is method 1 is better than method 2. Why? Yeah. So that's the reason why people use this relatively more complicated way to do it. So look at the swap operation. So you can see many times we consider the swap operations. Here we use 2 swap operation, right? 2. Here we use 1 swap operation. Although we use many comparisons, we use more comparisons than this case, right? Because think about, when we do swap operation, we may need to copy data stored in each node. So data, yeah. A node could store data, right? Data also store. So we need to do data copy. If the data size pretty big, then your copy operation is very expensive. Okay? Much more expensive than simple comparisons. Comparisons are very simple, right? Okay? Not very expensive. But if you make large data copy, that is very expensive. So that's why if we can reduce one swap operation, we should do it, because that can save a lot of time and resource also. All right, so our choice, method 1, and that's our 8.3. We have last part for this lecture, 8.4. All right.